In a world where the effects of climate change are clear and present, it is up to everyone to protect the environment. But the individual effort pales in comparison to the strength of efforts made by influential energy power companies. Strategies that produce efficient, low emissions for powerful energy technology companies are critical for the future of our planet. We analyze data from gas turbine engine factors to begin to identify potential advancements toward a net zero and sustainable energy future. We chose to restrict our analyses to outcomes at the power plant site level. Our rationale is that the scale is large enough to impact change at the level of one or many power plants, but small enough to hope to identify trends that can inform us of possible next steps for improving. Our first measure of interest was to complete raw pairwise comparisons of specific factors that may contribute to what is called thermal efficiency, meaning how much power in kilowatts comes from the power plant, divided by the product of the fuel flow measured by kilograms per second and lower heating value of the fuel measured by British thermal units per pound, multiplied by 100, the resulting value representing how efficiently the power plant produces energy. These scatter plots show pairwise comparisons from raw data and have not yet been corrected for multiple comparisons. These first scatter plots show the average power by the average compressor speed, the average power by the average fuel flow, and the CO2 emissions by the average operating hours. These results are intuitive and serve as a sanity check for confirming data analysis methods. These next scatter plots show relationships between the average power and elevation and the fuel flow and elevation. While these plots do seem highly correlated, it is important to remember that these raw data do contain outliers that might be excluded from traditional analysis methods, likely resulting in weaker relationships. However, in terms of a relationship between fuel flow and elevation, the inlet to the gas turbine is exposed to the atmosphere. Lower elevation means the atmosphere has higher pressure, thus resulting in a higher flow rate. Most interesting of our observations is this correlation with compression speed and thermal efficiency. This result is an important observation because compression speed is within the control of the operator. If power companies' goal is to increase efficiency, it is possible that increasing RPM may result in a higher thermal efficiency score. However, more research should be done to account for contributing factors that could influence thermal efficiency outcomes. We also wanted to know whether geographical factors could influence thermal efficiency outcomes. Geographical information was unrelated to thermal efficiency. And finally, we wanted to get a more detailed view of the individual level data. Here, we present the worst case scenario. As we learned, RPM may improve a thermal efficiency score. But this power plant should start by manipulating the RPM to attempt to improve their efficiency score. And here is the best case scenario we could gather from these data. This power plant has a higher RPM, which may be a contributing factor to the power plant having highest efficiency score of this dataset. However, thermal efficiency values range from 0 to 100. So while this score happens to be the highest in this particular set of observations, it is clear that all power plants in this set could benefit from improving their emissions performance. While certainly many factors are involved in improving the impact humans have on climate change, these data present evidence that more rigorous control of our effect on the climate is possible. Still, to address this specific goal, further analyses and continued data collection are required to improve our understanding of how these many factors affect the efficiency of gas turbines. We would very much like to thank the Texas A&M DATATHON 2022 organizers, as well as the MLH contributors, Baker Hughes for their interesting challenge, and Team Brainstorm, Josh Mashburn, Mocha Ono, Aaron Mock, and Molly McKinney.